Okay, this is the 4th edition of the Jam sort of lecture. It is evolving, I think, and I hope this will be the best one yet. Thank you, Obi, for giving some context to where this lecture is coming from. Just to get a show of hands, how many people here are like developers, like written a few lines of code and have pretty technical background? Yeah, about half. And how many have really very little technical background at all? Okay, all right, maybe a quarter. Fine. It's a bit of a technical talk, but I'm not going to get too deep into coding principles. So I want to start with a bit of trying to contextualize Jam further. So I'm not going to go straight into the Jam protocol, but I want to talk a little bit about the industry that Jam finds itself coming into. It is increasingly divided. We see increasingly teams, practitioners, projects, sort of selecting one of two paths to go down. Broadly speaking, they fall into those that were maybe sort of bought into the, Bitcoin and pre-Bitcoin mindset, very much sort of secure, resilient, scalable potentially, but sustainable. And then separately, the alternative path, of course, is a much sort of shorter term mindset, where people are looking for people are increasingly cutting corners in order to deliver perhaps something that isn't necessarily all that useful, but does make certain people money. Jam is very much on the left side of this. Jam is a project designed for long-term benefit. And I want to try to show that in this talk. There are some terms that maybe are not certainly associated with each other, but maybe people are not so sure about precisely how they relate to each other. Cryptocurrency, blockchain, often used interchangeably. DeFi has become a sort of major term also used in this space, and Web3, of course. They're not the same thing, right? DeFi is just a vertical in this whole industry. Blockchain is a means of solving a particular problem. Cryptocurrency is actually sort of essentially a resource. So you kind of characterize it in a couple of different ways, but one important way is that it's a resource. Web3 is the very much bigger picture, and it's an approach on how we solve large-scale social human interaction, right? And essentially, the approach is one that averts the need for trusted authorities or third parties. In some sense, it's the technological embodiment of the phrase less trust, more truth. So there's a few people have tried to sort of describe Web3 by, taking a few other terms and sort of saying, well, it's the concatenation of these things. It's the thing that, something that satisfies these things. The guy who authored these slides, Sean Tabrizi, that I've kind of altered a little bit to fit my personal take on things, has provided 5 there on the left. Andreas Antonopoulos, quite well-known Bitcoin advocate, has also provided 5, and those ones on the right are my sort of personal take on things, my 5. I'm going to go into my 5 a little bit more in a second, but broadly speaking, this is what Web3 is about. Simply because a project happens to be in an industry, have a particular market, use a particular technology, or call itself Web3, doesn't mean that it is legitimately Web3, right? And this is a bit of a point of confusion, I've noticed. I will often get asked, well, hold on, CryptoKitties, Pump Fund, these are all Web3, right? And it's like, well, no, not really. Do they fulfill these principles, these properties, these attributes? And in most cases, the answer is, well, no. In which case, well, it's not Web3 then. This is what Web3 is. So in some sense, Web3 is as I say, it's a different way of interacting with each other, with companies, organizations. And it's just fundamentally a more robust, resilient one. It's the model that we have at the moment doesn't actually work very well. It's oftentimes insecure. Things that people don't necessarily want to be happening to them happen to them under this model, under the Web 2 sort of model. And Web 3 aims to fix that by altering our approach to solving these sorts of problems that we have to solve. So what's blockchain? Well, blockchain is basically just a decentralized computer. Now, this is a bit of an odd thing, because a computer is, we're familiar with a computer, right? We hold one in our pockets most of the time these days. We tap on them when we're sending I don't know, email or whatever. But they're physical things, right? They're localized. My computer is here right now, right? It's like me. I can't decentralize myself. How can I decentralize a computer? But computers have a particular property. Broadly speaking, they're deterministic machines, right? We can model them with maths. And this means that we can build mathematical models of computers that don't actually exist in the real world, but are sort of held inside of other computers. We call these things, you're probably already familiar with one, like virtual machine, right? You might be familiar with the concept of a virtual machine. It's not a real machine. It sort of just sits inside your computer's memory and pretends to be a real machine. If you've ever run Windows on a Mac, then you may very well have been using a virtual machine. Really, all we're doing with blockchain is creating a virtual machine, but one that doesn't just sit in one particular computer's memory, but actually is somehow created or manifested over many different machines. Now, early versions of blockchain literally just replicated this virtual machine across many, many different computers, well, the good ones. But as we move forward and as we try to scale this decentralized computer, we can't replicate it on many different physical computers and expect them to be able to also process more data. It doesn't work. I'm going to get onto this in a second as well. But blockchain, when you hear the term, you can essentially these days just think of it as a decentralized computer, a decentralized model of a computer if you're going to be pedantic. Now we've seen, history tends to well, let's just say, it doesn't repeat exactly, but it often rhymes. We've seen the progression of computers, like physical computers, obviously started in the 50s, 60s, and then by the 90s, businesses were really utilizing them a lot, and eventually, they basically just become commoditized in the cloud revolution. We're kind of seeing something a bit similar play out with blockchains, right? Early blockchains were very domain specific. Bitcoin being the first one, highly domain specific computer, right? All it did was sort of process payments, sort of process transfers. And Ethereum sort of generalized this a bit with the EVM. But in essentially the same way that early computers, were initially built for solving very particular problems faster than a room of people could do it. And as they developed further, they got more general, and then as they developed further still, they became effectively commoditized. The same thing is almost certainly going to happen with blockchains, which are just decentralized computers after all, therefore probably will follow the same path. So if we look specifically at the protocols, see Bitcoin was basically a calculator, domain-specific computer. And Ethereum comes along and sort of generalized this into a more or less general purpose computer. And I say more or less, this is being quite charitable. but there are elements of it that were notably general. Polkadot, on the other hand, is moved this forward. It's sort of creating, let's say, a cloud server, but like in reality, the initial Polkadot, sort of this relay chain, parachain model, was probably more akin to a sort of a local area network, a networked set of computers, in that the computers each ran independently, but they could send messages between themselves. And I'm going to go into that a little bit further. So the real difference between the Web 2 approach and the Web 3 approach is one of resilience. If it's not resilient, then it's probably not Web 3. There's a lot of things that digital systems need to be resilient against. It's not as simple as just trying to make something resilient against a particular situation or a particular malicious force like we would normally do with this sort of thing. One of the very interesting characteristics of Web3 systems is that they have to be resilient not merely from the perceived malevolent forces in the world. They actually also have to be resilient against literally everything, including possibly benevolent forces, or at least presumed benevolent forces, forces that could be presumed to be benevolent. An example of this would be its creator, right? Web3 systems, unlike Web 2 systems, like basically anything that's come before, need to be resilient against their owner, their creator, right? The thing that brought them into the world. Now, normally, if a company sets up a server, right, they own the server, they created the server, they expect the server to basically do exactly what they want to do, right? They are the single point of authority over that server. There is no need. In fact, it would be considered maybe not even just a waste of time, but actually problematic for that server to become resilient against the company that ran it. Yeah, that would be unthinkable. Why would we do that? They're the ones that created the thing in the first place. But we have to do this with Web3 systems. We have to create systems that are resilient, not just against other Web3 systems, Web 2 systems, all sorts of whatever. Actually resilient against those that created them in the first place. And this is often forgotten, but it is very important. So how do you build a Web3 cloud? Well, basically you get powerful Web3 decentralized computers, blockchains, and you sort of put them together as you probably would a regular cloud, and you make some fast decentralized networking equipment, right? And in the end, you end up with something that is essentially a decentralized version of AWS or whatever. This is what we would, a sensible approach, I would argue, for building a Web3 cloud. Now, the key issue with building a Web3 cloud, of course, is, well, where do we get that initial very powerful decentralized computer from, and where do we get the decentralized networking equipment from? And these have to be protocols, right? We're not talking about physical networking equipment. We're not talking about a physical computer. We're talking about a decentralized computer. And first things first, let's see if we can come up with an effective decentralized supercomputer. And this is really where Jam is coming from. So what is it that we call computation on the decentralized computer? What is this stuff called? Because it's not the same quality of thing as computation that this laptop specifically does, right? This laptop, yes, it does computation, but in some sense, all it's really doing is helping me do computation. It's really just me. If I tell you that it had some particular answer, like I might be lying. I might just want you to think something. You have no idea actually what my laptop said. Yeah? It works through me because it's my laptop. And this is necessarily what you have to do if it's a physical computer. Yeah? It's under someone's control, under someone's ownership. So really, it's that person you're trusting, not the computer. And this is the problem. And this is the problem that decentralizing things fixes. Yeah? So if you run software on AWS, you are in fact trusting Amazon to run your software, and you're trusting Amazon that the results are correct. You don't realize this, of course, because they put a very pretty face on it and they give you, apparently immediate access. But that is the relationship. It's one of trust. Yeah? You have no great reason. You have to have some faith to believe that, especially if you're doing very, very economically sensitive things on the AWS, that it's actually working correctly. So block space is this term that we use to give to computation that's done on a decentralized computer, as opposed to computation that's done on a physical, specific instance of a computer. Block space is the Web3 version of cloud computing. Now, Web3 is a bit of a kind of fuzzy term, because although we know sort of the principles of Web3, it's potentially quite hard to measure how much something is Web3. It's not like a black and white thing. There are some protocols and projects out there that are not that Web3. I mean, they're a bit Web3, right? But they're not very Web3. So we need a way of measuring how Web3 something is. And there's a few different aspects to this. And here's 3 of them that are named: quality, availability, flexibility. I mean, there are a few different things, and I want to sort of show you that Polkadot, even as it stands, is the highest quality block space. So in terms of supposed throughput, I mean, transactions per second is a pretty awful measure of things, but it's unfortunately what the industry seems to be pretty fixated on. In reality, we should be actually doing proper computation benchmarks, right? Something akin to IOPS per second, something akin to like, floating point, well, maybe not floating point, integer operations per second. But anyway, we have TPS. There we are. So this number comes from a live network. All the numbers come from like actual live recorded max TPS throughputs. And this is actually using Polkadot protocol, but on the Kusama network. We have huge data bandwidth on the Polkadot network. More so even than multiples of domain-specific data availability systems. The Nakamoto coefficient of a system is essentially the number of independent economic actors that would need to be compromised, hacked, colluding, or just malicious in order to compromise the system itself, the decentralized computer. Polkadot has by far the highest of all of the major projects. And it turns out we're actually super energy efficient as well. This is essentially because we scale out rather than trying to just beef up the machines. As you beef up machines tend to use more power, right? Whereas if you're able to scale the computation, the processing out across many lower power machines, you end up substantially using, in aggregate, substantially less energy. So yeah, one of the ways that we manage this is by parallelization, execution sharding, data sharding. Essentially making use of more smaller, more modest hardware instances. And we also managed to pool security together so that in principle, each of these execution instances, each of these sort of models of a computer can exist in the same economy, right? They can strongly interact with each other. Sometimes you need useful ways, useful data formats to facilitate that interaction. This is something that Polkadot pioneered as well with XCM, its cross-consensus message format. And of course, you need some sort of storage for your blockchain computer, And this is what we mean by data availability. The storage, crucially, must be as decentralized and as secure as the computation itself, the processing. If it's not, then it's not going to work. It's kind of like having a broken hard disk with a really fast CPU. So, JAM. JAM has already been sort of accepted by the Polkadot governance system as the next iteration for Polkadot's technology. It's specified in a paper called the Gray Paper and built by many different teams. Decentralization, resilience, diversity happens not just in terms of having lots of nodes on a network. It also means decentralizing and diversifying those who understand how the protocol works. Protocols, possibly Bitcoin notwithstanding, evolve. And they can only evolve effectively if, and in a decentralized manner, if that knowledge, the understanding of the protocol, the comprehension of how it works and where it might go, is itself decentralized. If you have a single team that knows about the protocol and the software that runs it only, then you're going to be compromised and you will not be resilient in the sense of Web3. All right, so the approach with JAM is, and always has been, quite different to the approach with the Polkadot relay chain and parachains, Polkadot 1, if you like. Whereas Polkadot was created, in a sense, software first. The software was written before the protocol was really fixed. JAM takes the opposite approach. The protocol is fixed before the software is written. This allows many different teams to create interoperable but competing implementations, driving forward essentially both technical diversity, geographical diversity, and decentralizing and distributing that knowledge that is so important to keep the network resilient and to make sure it's long-term. Those who read the Gray Paper, it's, I try to make, there's enough English in there that it should be readable even to people that are maybe not super technical. There are formalisms as well, so there's quite a lot of maths in there. But the formalisms, for those who are already familiar with the yellow paper, the Ethereum formal specification that I made back in 2014, will be reminiscent. There's a large prize pool for those teams implementing the JAM protocol, 10 million DOT. This is probably the biggest programming prize in human history. At the moment, there are 35 independent teams working on implementing this protocol, using over 15 different programming languages. Again, this is a level of decentralization that blows anything in the past out of the water. Yeah? In order to make this protocol fast, despite there being lots of different teams with lots of different implementations, unlike anything that, to my knowledge, that's been done before, we have a perfect model of the final network being built in a sort of custom-made facility. Now, essentially, all of the hardware, all of the independent machines, physical machines, that would require JAM, that JAM would require to run. By creating this in one place with one operator, which sounds very centralized. Of course, this is just for debugging, experimentation, and testing. It's not for production. But by creating this sort of centralized version of JAM, we're able to do experiments that would be very difficult, if not impossible, on a regular testnet. And we're able to see things like emergent effects, integration effects from the different implementations, measure the discrepancies between our theoretical models, and investigate those discrepancies, and essentially create a series of implementations, a set of implementations that work according, or as best as is possible to engineer, to the theoretical models. This is something that we had some issue with Polkadot, because essentially we couldn't investigate so easily. Yeah, if the testnet is being run by umpteen different validators, or even worse, if it's just the production network that manifests the issue, it's really hard to investigate. You don't have the logs, or the logs are in different formats, or they have different logging options, or they've deleted them, or whatever. It's hard, but with the toaster, we hope to make it easy. It's actually quite a substantial compute machine. It's far more powerful than this laptop. It's not, you hear mad supercomputers being built these days, like GPU supercomputers. It's not going to compete with any of those. But it is a substantial machine that we're talking about, like 16,000 Threadripper cores and an awful lot of memory storage and networking. All right, so that's the approach that we're making with Jam. What is Jam? To help you understand where I was coming from with the Jam protocol, I need to talk a little bit about these 5 principles of Web3. Now, Web3 systems have to be resilient. If they're not resilient, they're not Web3, right? So that's the first thing. And Web3 systems to date have been resilient. The first one, Bitcoin, I mean, actually, you can trace Web3 before Bitcoin. Like BitTorrent is very clearly a Web3 system. It agrees with the vision set forth in 2014. But Bitcoin as a blockchain, resilient. I mean, it's still going. The fact that it still exists and it's still doing basically what it should be doing is, or it was meant to be doing back in 2008, means it's resilient. It's not general and it's not performant, but it is resilient. Ethereum comes along and basically takes Bitcoin, but makes a more general purpose computer, more general purpose decentralized computer. It's still not performant, but it's now got the top 2 things, resilience and generality. Polkadot comes along, it keeps resilience, keeps generality, and it delivers performance, right? As you can see in the crazy high TPS numbers. Now the thing is that when we were developing Polkadot, we assumed, well, we didn't really think too hard about it, but I suppose in the back of our heads, we were assuming that coherency wasn't so important. The level of coherency enjoyed by Bitcoin and Ethereum wasn't so important, because Polkadot scaled out by essentially splitting apart the different elements of the whole system state into independent sort of portions that each move independently of the other. This is how we scaled. This is how we got that good performance. And so, in essence, reduced its coherency. Jam aims to set us on a path where we don't have to reduce our coherency noticeably in order to get those first 3 things, resilience, generality, and performance. So if we look at the past work, right, Ethereum 1, unscalable, right? It doesn't, it's limited in what it can do, very limited. I've done a little picture there. So the dotted line in this picture is like the validators, right? It's like the sort of set of validators that are validating. Ethereum only has one set of validators, and they're sort of validating. And then the thicker line in the middle is meant to be sort of the state of the system. There's just one state, right? It's the state that all the smart contracts live in. So some of the things that have happened since Ethereum has launched, well, one of the things is that people have tried to take this model and basically beef up the servers, right? And improve some of the networking elements, optimize the software, and so forth. Essentially keeping the model, but trying to make it go faster, process more stuff, take in more data. And what we found is that these, if you like, optimized Ethereums, of which Solana is a very good example, tend to centralize, right? Tends to result in substantial centralization, substantial additional fragility. That resilience is seeping away, and ultimately the fastest that these systems can go, these sort of single state synchronous systems, is about as fast as like one server could possibly process things. Right? So in order to make them go faster, you just have to keep upgrading your hardware. Now, of course, hardware gets better over time, but we're not going to see dramatic changes from aside from Moore's law of things just sort of increasing in hardware. Really what we want is a way of not scaling up, but scaling out. So one of the ways that people have tried to scale out, particularly in the Ethereum ecosystem, is by having roll-ups. These are essentially means of magnifying or compressing, depending on which way you look at it, computation. The point of a blockchain, of course, is block space, and block space is really just correct computation. Computation which, regardless of what any particular economic actor wants to happen, will be correct, right? Resilient computation. Now, if you can essentially magnify the amount of correctness that you do, or compress the concept of correctness into a smaller amount of computation, then this allows you to scale, potentially scale out a lot. So one of the things that Ethereum's been working on, I say Ethereum, it's like the whole Ethereum ecosystem, is roll-ups, or sort of compression of computation onto the Ethereum chain. And the problem is that lots of people have taken lots of different directions with roll-ups, and a lot of the technologies are a bit unbaked. One of the technologies that's being used is what's called optimistic roll-ups, which I would rename pessimistic roll-ups because they take a very pessimistic view of the world, where essentially they, computation is purported to be correct, and then you get, like, I don't know, 4 days or whatever to prove, for anyone to prove that it's not correct. So which means for 4 days, it's just sort of in this limbo of like, kind of pending, it's probably fine, but might not be, you don't really know. Nothing really happens outside of that little piece of state until this time has passed. In general, the roll-up landscape is patchy. Different roll-ups have different sort of security parameters, centralization parameters, latency parameters, potentially different versions of the underlying virtual machine. But one crucial thing on the roll-up path is that we end up with this state partitioning again. We see this again and again. State, the overall state, including all of the roll-ups, is sort of partitioned up. And in one partition, there's like the original Ethereum chain. In another partition, there's like one particular roll-up state. In another partition, there's another particular roll-up state, and so on. And if you're happen to be on the same partition, it's all good. But if you're in different partitions and you want to interact, everything becomes difficult and costly and slow, right? Essentially, we're breaking our network effects. It's problematic. In the case of using some of this exotic cryptography, zero-knowledge proofs, we also see a huge centralization effect, right? The systems become biased towards there being very few actors, each with a huge amount of sort of invested resources that are attempting to provide the service that they're providing. We see, to some extent, a winner-takes-all economy forming. Yeah? And this is hugely problematic for if we want to be agnostic to the data that makes its way on chain. So another approach has been what I've called like homogeneous bridge chains, of which Cosmos is a good example. So this is also a sort of attempt at scaling out, but rather than scaling it out under the same economy, what we do is we scale out just with different validator sets. So you can kind of see here, I've drawn the different validator sets in different colors, each securing their own little bit of state. Yeah? And then transactions sort of go into their particular area of state, do something, and then we have these bridges that connect them. What's the problem here? Well, the problem is that they don't exist under the same crypto-economic security mechanism. So if one part of this system gets broken, then that breakage seeps into the other part. Now, some of this seepage can be controlled. You can maybe limit some of the, what I would call causal toxicity that is coming from a poisoned network. But overall, economically, it doesn't really scale. As you add more and more networks, you're essentially dividing up that validator resource, that capital that is backing and backing the computation and making sure that it's correct. Essentially, you're dividing a very important resource amongst the different chains, where actually what you want to do is pool that resource. We also see persistent state partitioning, right? You have to choose which bit of the overall state you want to deploy your thing into. This is problematic. And we also see some high barriers to entry. Developing a blockchain is not a trivial thing. Deploying it is not a trivial thing, compared to, say, just developing and deploying a smart contract. Coming on to Polkadot. So this is sort of Polkadot 1, relay chain, parachains. Now, Polkadot's main advantage over the bridge chains model is this shared security umbrella. Yeah? This allows each of the different economies to share in the same security guarantees, the same crypto-economic mechanism, the same capital pool. However, the other 2 points still stand. We see relatively higher barriers to entry compared to smart contract deployment and development. This is coming down, but it's still there. And we also see a persistent state partition. The different parachains have their own state. Now, of course, they can talk, they can interoperate with each other. There are formats, like, as I mentioned, XCM, that facilitate this interoperation. But at the end of the day, they are still different state machines, and they're hulking great ones as well. Like, they process a lot, they hold a lot of data. And this makes it hard to compose across them. Why did it end up like this? Why didn't we just make it both kind of decentralized and able to sort of scale out and have high degree of cohesion? Well, it's a pretty fundamental problem, actually, it turns out. It's called what I'm calling size synchrony antagonism. But basically, as a system grows, the independent parts of its state become, on average, further apart, and the distance, the variance of any two distances between the state items increases as well. So they're further apart, but also sometimes they might be closer, and sometimes they might be farther away. Yeah, and that divergence increases. This is this leads to what we call, or what we might call, a reduction in coherence. It becomes harder for the system to retain a coherent state. Either it goes slower, and we basically make everything go only as fast as any two parts of state could possibly interact, essentially slowing everything down for those bits that are actually close together and could interact faster. This is what, for what it's worth, they do on CPUs, right? So on CPUs, when they're doing this, they actually make some of the circuits, the sort of bits of silicon that are connecting portions of the CPU, longer than they need to be, just to keep everything arriving at the same time. Keep that coherence. Yeah. We don't really want to do that with blockchain. That would just make everything go very, very slow, and there'd be no point of scaling, or less point in scaling. So how do we manage it? Well, so far, we've managed it basically by splitting things up and just saying, well, if you happen to not be in the same area, then you just have to send a message, and that message is going to be asynchronous, right? Essentially, we say, this bit is coherent and this bit is coherent, but these two bits, they're not so coherent. Okay, I'm going to give you some pictures. I drew these pictures quite recently, so they're still a little bit rough, but I hope they will help explain what I'm talking about. So this is a picture of what it is that we want. The outline there is the state of the system. As you can see, there's one state. This is what we're after. This means that any two parts of it can interact as they want. The arrows going down are, if you like, objects within our state, and they are proceeding. The fact that the arrows go unbroken means that the objects just have their own thread of execution. Yeah? So they can just, if they want to do an infinite loop, they can do an infinite loop. This is regular software. That's a property that we quite like. If you like, if you're into programming languages and whatnot, this is a bit like an actor-based environment, right? So we have lots of actors, each sort of proceeding and interacting as they need. They exist in the same state space, which means they can all interact just as easily as each other. That's kind of what we're after. This isn't possible. If we expect to be able to scale, this isn't possible. This is just the ideal. It's what we're striving for. Yeah. And obviously, I drew, I don't know, whatever, 9 arrows or something. We want lots of arrows, yeah? We want as many arrows as we expect there to be smart contracts or actors or whatever. Yeah. I just had a limited amount of time, so I only drew 9. This is what we've sort of been experimenting with so far. On the left there is kind of Ethereum, right? So in Ethereum, the actors are smart contracts, and as you can see, the arrows, the execution sort of flits between the different smart contracts, and we only execute one at a time. Yeah? So we kind of do a little bit of one, and then we move over to do a little bit of another, and then we go whatever. And then actually, we spend most of our time doing nothing, right? Because in Ethereum, we're pretty conservative about how much time we spend in a block, in any given block period, executing, because we sort of want to reserve time for sharing the block around the network. It's better than it is in Bitcoin, right? In Bitcoin, I don't know, process a block in, a few seconds, but it takes, on average, 10 minutes for a new block. So we have this really, in Bitcoin, very, very bad percentage, like efficiency. In Ethereum it's better, but it's still pretty bad. I think, I calculated it at one point, I think we spend, at most, if it's like the worst possible circumstances, about a second out of every 12 actually using the CPU. The rest of the time, it's idle. Now, as I said, there are ways of optimizing this, and networks like Solana have optimized it. They've optimized it in many cases quite well. But it's still basically the same model. I made the arrows a bit thicker because some of these systems are doing things like multi-core, like multi-CPU core utilization. So it can actually use more than literally a single CPU thread. But still, everything's inside one machine. We're not scaling anything out yet. And so in essence, we're still limited to this sort of essentially synchrony of only doing one thing at once. The middle one there is bridge chains. And this is where we sort of split apart our state, right? And we split apart our state, and then we have sort of bridges that can send messages across state, usually with some latency, which is why those lines are sort of skipping a block. Now, in this case, the blocks, I've drawn the arrows as a block rather than actually pull it out into smart contracts, but each one of these like single line arrows could be decomposed into what's going on in the first two with like different smart contracts running. But with these, the last two diagrams, in reality, the sort of atom is a blockchain, not a smart contract. So it makes more sense to draw these big arrows. Now the arrows still stop. It's very important to realize that I didn't draw one big arrow going down, because at the end of the block, you kind of have to pack up and leave, yeah? And then only when the next block starts, you can start your computation again. The one on the end there is Polkadot. Now Polkadot, again, has this like shared security model, so everything works under the same security umbrella. But we have these lines going down, these bars going down in the middle, indicating that the state space is partitioned, yeah? And it's a fixed partition. And within the state space, we get the nice arrows, yeah, going down. But they can only sort of send messages to each other. If we want the two arrows to sort of collaborate on some work, maybe one of them is a DEX chain and the other one is, I don't know, a token hub, we have to sort of send messages between them. The fact that we have to send messages means, generally speaking, atomicity is either impossible, impractical, or expensive. So this is Jam. This is using roughly the same visual language. And we have, what you'll see first is, well, there's a dotted line around Jam. So everything is under the same security umbrella. And we have this funny structure with Jam. It looks a bit like a flower. We have a bit in the middle where everything kind of comes together. This is the synchronous part. And then we have the petals. And each of the petals is where all the real hardcore computation happens. But crucially, the petals exist in a shared state. Each of the petals is more or less fungible, which means computation that starts on one petal can continue on another petal without any special affordances of data transfer. The bit sort of that the petals are sitting in, if you like, is this decentralized availability, distributed availability system. So to take this to the other sort of visual language, Jam has this bit on the right, which looks quite a lot like what we had with Ethereum, if you remember. But then it has this extra stuff on the left. I'll just rewind to the Ethereum thing so you can see. So it looks a bit like what was going on in Ethereum, right? It's optimized. So we do use a lot, actually most of the block period for computation. And the machine that we use is very fast as well. But it's still synchronous, yeah? We're still only doing one thing at once. We need this in order to retain some degree of cohesion, at least without a compute model that would do that with parallelization. So on the left, we have this additional stuff. Now, at the very left is our decentralized distributed data lake, very large DA system, stores in excess of a petabyte of data. And then in the middle is our if you like, our coprocessor system. These are stateless machines, but they can read from this distributed data lake and write to it at the end. Now, the reason that the data lake only has a thin line is because it's not fully coherent. In particular, its model of storage is really just cryptographic commitment. It's immutable. Right? You can't change something that's already in it. So you can't really store anything sort of stateful in there. It wouldn't make sense. But what you can do is store data, large amounts of data. In some sense, it's like a data magnifier. If you know what you should be looking for, but it's only very small, it's like a hash or whatever, then you can ask the data lake to give you the pre-image, and therefore increase the amount of data you effectively have. If you notice, the arrows are sort of they come from the data lake and go into the data lake, and then they also go into the bit on the right. So you can think of it as a preprocessor, coprocessor, but very high compute and bandwidth capacity. That's introduced the concept of cores. Cores are each of these execution threads in the middle. Each one of those big, thick arrows, and it's very thick because actually these things are online the vast majority of the time. Out of every 6 seconds, we would expect 5 seconds to be used by each of these, right? So we're really ramping up the amount of processing that we can do, in part because everything is pipelined and asynchronous. We can actually do this. So each one of those things is a core. Jam has not just 4 of them, it has 341 of them. And Jam, as you can see from the previous diagram, splits the computation that it does and says, well, the bit that needs to be fast and have lots of data bandwidth, we're going to make that stateless because that allows us to have lots of them. And then there's things that need to be actually synchronous and stateful and fully coherent. Well, we'll allow that sort of to be slow, but we'll connect them so that you can send data from one into the other. As I mentioned, there's 1.6 petabytes of data able to be stored securely in its data storage system. And there's a 6-second inter-core synchronization latency, which means data that is written by one core will be available into the other cores 6 seconds later. If you're in the same core, it's available immediately. Nothing incorrect will ever happen. So if you happen to be, I don't know, switching to a different core where you're expecting data to be available that you just wrote in in the previous sort of slice, time slice, all it means is there will be a slight delay to your computation, like 6 seconds. But it's not going to do anything wrong. It's not going to say, oh, the data's not there and I don't know anything about it. It will just basically hold off until it's sort of synchronized. This is, for what it's worth, quite similar to how physical CPUs work with their memory coherency. The data lake itself works in 4 kilobyte segments, and it's a cryptographic commitment. As I said, it's immutable. So maybe some of you are more familiar with Ethereum terminology. If we like, we can reimagine Jam as sort of an Ethereum chain, right? But one with what Ethereans might call native rollups. Yeah. We have this Turing-complete smart contract L1 chain. That's the Jam chain. And then we have all of these native rollups, L2s, 341 of them, each doing their thing and sending data over into the L1 chain. And they have a DA store that they can access, write data in and read data out from. This sounds quite similar now to what some have been proposing quite recently in the Ethereum community, I think. So how do we achieve it? Well, we have a few different technologies we're bringing to the table. One of the technologies, the first one, is our roll-up technology, right? It's the way that we actually make sure that these cores, these extra co-processing units, are secure. Yeah? That's how we ensure it's legit block space. The protocol specifically is called ELVs. I like to think of them as cynical rollups as opposed to pessimistic rollups. In essence, we don't just fit the tires onto the car and wait 4 days to see if they burst. We actually make sure people go up to the tires and kick them. Yeah? Because just waiting for them to burst within 4 days seems really dumb when you have a foot and you can just kick the tires. And, you know, realistically, if you're going to kick them and you get enough people to kick them that you believe at least one honest kicker had a good go at it, and it didn't burst, then it's probably fine. You know, we gain confidence. But we are proactive in our attempt to gain confidence that this computation was correct. We don't just sort of sit around for 4 days, yeah, and wait and assume the worst. We also have a zero-knowledge proof-based block authoring system. This is new. This is called Safrole. And it averts the problem of giving away the identity of the next block author until they're already distributing their block. Now, this is a fairly important thing for resilience. Some attacks on networks can be pivotal on the ability to block transactions or block the network from doing anything for a block or 2 or 3. Yeah? Now, if you already know exactly who is going to author any given block at any given time, then you can, and you have enough resources available to be able to spam them, or maybe you know a hack for that particular implementation that take it down, make the node crash. Then you can pull off your attack. Yeah? You can stop the network from doing something for a while. Safrole makes that really hard because we use zero-knowledge proofs. so that the next block author can demonstrate that they are the single legitimate block author of this block without anyone knowing who they are beforehand. Grandpa, already in use in Polkadot, gives adaptive and near instant finality. Adaptive finality, what's that? Well, basically, finality is a substantial toll on the network. It requires all of the nodes that are taking part in it to basically congregate and all send messages to all of the other nodes. So it becomes an order n squared networking problem. All the nodes sending messages to all the other nodes. This is if it's secure. There are networks that cut this corner, but they're not very secure. We want to be secure. Now, if the network is congested, it will take longer to send these messages, receive, and then come to a consensus opinion on what everyone thinks the final block is. What Grandpa does is it manages to make this adaptive, which means the time, while it may take the same amount of time to come to consensus, we can, if the block is going further, because this time is extending and we're extending the chain sort of faster than we can finalize the last block, Grandpa allows us sort of a graceful degradation where we just finalize the latest block that everyone can agree on without having to actually have separate rounds or separate consensus conversations for each different block. Finally, we have a new technology, very new technology, PVM, based on an older technology, RISC-V, but with some alterations made to make it very effective for the job that we want to do. So if you're not familiar with RISC-V, it's an open source instruction set architecture. It's made by an academic, designed by an academic, and it's supported both by hardware manufacturers. There are physical chips that run RISC-V code, and compilers. It's like considered a primary supported target for some compilers out there. LLVM targets RISC-V, which basically means C, C++, Rust, the usual suspects can also target RISC-V. Now we have a RISC-V to PVM recompiler that basically just makes the various tweaks that need to be made to turn RISC-V code into PVM code, allowing PVM to be targeted essentially by all of these languages. That's why I say it's normal. It's like you can use normal languages. It's a normal type of instruction set. It's fast. Now you don't need specialized hardware to make it fast because we have an x64 recompiler. This recompiler takes any PVM program and with order n, so single pass, linear time, turns it into x64 code that's ready to run on AMD, Intel, whatever. Yeah, we actually also got a RISC-V to ARM recompiler as well that has similar profile. This is game changing because it means that by moving away from the highly domain specific code with various highly domain specific languages into a regular software development mindset and framework. It also means that we are able to execute code at roughly, I mean same order of magnitude, that of native. Yeah? I'll talk a little bit more about this in a second. So the jam pipeline is basically 3 stages. Here they are. First, we authorize that the computation is allowed to be done on jam, right? This is the anti-spam mechanism. It's what you pay gas for on Ethereum. It's what you used to have to do a crowd loan for on Polkadot and now have to buy core time for on Polkadot, right? Anti-spam. Our authorization mechanism is actually very, it's Turing complete. You can literally write any code you want to authorize work in any way that you want. We don't fix it to be, you have to pay gas or you have to do this or that. Now, of course, you have to by the ability to authorize work to be done, and this would happen on the machine's native token. But the authorization itself can be totally flexible. After the work package has been authorized, it now hits refine. This is the thing that happens in core, and it's lots and lots of bandwidth, lots and lots of processing power, but stateless. After refine, its output is sent on into accumulate. This is what happens on chain. It's fully coherent, synchronous. The authorizer code is different to the service code. You can think of the service code basically like smart contract code, right? Except unlike smart contracts, it has two entry points. Refine, that happens in core, and accumulate, that happens on chain. Authorizer code only has one entry point, the authorization itself. So shared state in Jam is arranged into services, and they all exist in the same state. Yeah? We have not yet partitioned state. Jam can be used to do things like validate parachains, which probably are then going to partition state. That's the parachain model. But at this point, Jam, we have averted partitioning. Yeah? This is a good thing. This gives us some flexibility with how we utilize this model. So what's the difference between Jam services and smart contracts? Well, the first thing is that there are different stages of computation in Jam services. In the smart contract, there's only one stage. It executes. Yeah? In Jam, computation has fundamentally different execution environments. Refine, then accumulate. This is pipelined, which is a way of saying that accumulate can execute at the same time across the Jam network as refine for that same service is executing. Yeah? Like refine and accumulate are fundamentally parallelizable. Yeah? But moreover, refine itself is distributed. A single service can have many different refines running all at the same time and pooling their outputs into accumulate, which of course is synchronous, so those outputs would have to be, sort of taken, quote unquote, one at a time in serial, right? In series, synchronously. This makes Jam generally asynchronous, unlike smart contract networks that tend to be synchronous. There's also, unlike smart contract networks, bulk purchase of this fundamental resource. In the Polkadot ecosystem, we call it core time because it's time on a processing core. In other more industry neutral term would be block space. And if we're talking about Ethereum, we would say gas, right? But this resource is purchased in bulk. It can then be split up, resold, secondary market, whatever. But we buy it in bulk. We don't talk about sort of individual little bits of, well, we do talk about it, but not in the context of actually purchasing this resource. Jam's permissionless. Anyone can put a service onto the Jam chain, just like a smart contract chain in that regard. Yeah? Anyone can upload a service. And services don't have, like, artificial limits placed on them. The limits come as, in terms of economic disincentive from being, or in economic cost from being, overly profligate with the resources. So, for example, as you place more in storage, you're required to have a higher balance in your service. The service just has to have a higher balance. Yeah. If you don't place so much in storage, then you can get away with a lower balance. If you place lots and lots and lots of things in storage, you need a higher balance. Same with code. An example of a service would be Polkadot 1, like the relay chain. That would be a whole service. So you can start to see services are very powerful things. And the reason they're powerful is because we have this huge coprocessor network kind of attached and sitting under the same security umbrella. This makes services potentially incredibly powerful. Jam doesn't care about the higher level blockchain stuff. Jam's agnostic to it. You can implement this stuff on Jam for sure, maybe even in Jam services or maybe on blockchains that sit inside of the parachain service. But Jam is agnostic to what they do. Staking, economics, governance, Jam doesn't care. Let's talk a little bit about the Jam PVM because it is a very important aspect of Jam. So, as I said, it's an instruction set architecture based on RISC-V. RISC-V code can be turned into PVM, which allows us to use all these compilers. It looks like a regular machine, right? This is really important. If you look at EVM, it doesn't look like a regular machine. It's pretty mad, like cryptographers' vision of a machine. PVM is essentially a simplified, vaguely hardware-neutral version of a modern silicon ISA. It's Harvard architecture, that's a little different. So it stores its code separately in a sort of ROM, separately to the main address space. What this means is that you don't have to worry about accidentally overwriting your logic in a PVM program. That class of errors and bugs can't happen. It has a 32-bit address space, right? Normal software runs on this thing. It's paged 4 kilobytes. Again, like normal software runs on this. 64-bit registers, not 256-bit registers. Yeah? All of this stuff means that recompilation into regular silicon ISAs like x64 can happen really easily, really fast. Even if we take the recompilation into account, when we're running code on the PVM, we get minimal overhead from actual native compilation, maybe about 45% of native execution speed. Right? This fundamentally alters the kinds of software that you can run on chain. It fundamentally alters like the development profile of writing software that runs on chain. We don't have to think too hard about, how we're going to fit a particular data structure in memory. Map it to this random 32-byte to 32-byte Merkle tree. Now, one very important thing is that we get an addressable stack. Our stack sits in addressable memory, which means if we can store all of the pages in the DA system, in the dynamic distributed data lake, and I'll remind you that the segment size of this data lake happens to be 4K, then it means that we can suspend an instance of the PVM and then restore it and restart it later in another block. This is a bit of a sort of diagram I drew a while back. It's maybe not so helpful, but basically on the left side there you have the core, the in-core thing, like this very fast processing unit that has 300, that Jam has 341 of. This is why we call Jam a supercomputer. It's got 341 near-native processing cores, right? This is bigger than a lot more powerful than that laptop. And then it also has this like big data throughput. 2 megs a second goes into this core, and the core can output 2 megs a second back out into the storage system. And then we have this, what amounts to a kind of very scriptable synchronous database that is on the on-chain part, the accumulate part, that this core can interact with, give data out to. As I said, refine can generally execute for 5 seconds in every 6 of PVM gas. So if we're talking about native, it's maybe about 2 to 2.5 seconds of native x64 computation every 6. It can do a bunch of stuff, but main thing is it can accept 12 megs of data from the DA or from that's just totally extrinsic to the system, and it yields up to 48K that goes into accumulate. And accumulate is a stateful thing. Now, one important point here is that refine can invoke new instances of the PVM. New virtual machines can be created in Refine and executed. This is a big deal. This allows a certain thing to happen that has not yet happened in blockchain. Actual Turing-complete code. I'm not going to go too much into the authorization system. I think that's probably too technical. I want to talk a little bit about why JAM is a sensible proposal at all. Because it looks, when you look at that architecture diagram, it looks kind of complicated. It's like, what's going on here? Why are we complicating things so much? Well, partly because we have to, right? This is just how we skirt around the coherency, scale coherency problem. But JAM is being, in part, designed to be able to run Polkadot's parachains. But it's also being designed to be run a next-generation smart contract system called, codenamed Coreplay. Before I get too deep into Coreplay, I really want to point out what it is that L2s or extra blockchains or parachains or whatever solve. What are we trying to solve here? Now, I'm going to argue that actually some of the things that we've sort of said in the past that we're trying to solve are not actually that important. They can still be solved in an adequately flexible and powerful smart contract environment. Specialization, one of the things that blockchains was meant to solve. We can do in an adequately powerful and flexible smart contract environment. Sovereignty, ditto. But one thing that we can't do, really, is scaling out. That's why we have more, that's why L2s are a thing, that's why parachains are a thing, that's why multiple chains are a thing. So it's hard to scale out a single state transition system. And the big problem with that, as I've said and tried to sort of nail, like really hammer this in, is fragmentation. We fragment our state space, we have to partition it. Why is that a problem? Limits network effects. Yeah, this is a big issue. Limits use cases, limits atomicity, developability. And if you're a team that are looking to deploy, it forces you to choose an avenue, choose a sort of a cul-de-sac of blockchain where you're going to be able to interact within that cul-de-sac nice and quickly and relatively cheaply and maybe atomically. But doing those things with any other cul-de-sac, stuff in any other cul-de-sacs is hard or slow or expensive or all of those things or impossible. Let's go back. Let's rewind. This is what we wanted, and I told you this isn't possible. Yeah? Size synchronicity antagonism prevents this from happening, just fundamentally. This is what we are aiming for with Coreplay. Now, you'll notice the arrows are unbroken. Yeah? This is unlike anything in the past in blockchain. The arrows have always been broken. There's always been a limit to the amount of computation we can do at a time. With Coreplay, the proposal is, let's lift that limit. Let's make it actually Turing complete. So you can write arbitrary code, just regular software. You want to run Windows on it? I mean, notwithstanding the fact it doesn't have a screen, go ahead. You want to run Doom on it? No problem. We're developing this. I've already seen the first frame of Doom rendered into the DA on PVM, on a JAM network. Now, the purpose of Coreplay isn't to do the impossible. That's impossible. But it is to alter how we manage the fact that we can't have full coherency in a scalable system. And all we're really doing, and it stands to reason, it's pretty obvious when you think about it, is rather than having these bars going from top to bottom, partitioning state or sharding state in a very fixed fashion, we instead make the bars temporary, transient. We group together bits of state that need to be together at that time, but we don't force them to be together at any other time. We're being agile in how we partition. Yeah? So JAM itself is a sophisticated protocol. It's complex to write software for. But one of the pieces of software that we will write for Jam, because Jam averts this fundamental partitioning, fixed partitioning. So one of the pieces of software we want to write for Jam is CorePlay, which will allow us to make an easy platform to write software for. Something much more similar to smart contracts or actors, but one that is fundamentally elastically scalable, so it can scale out across Jam's cores. This really quite substantial blockchain supercomputer. So CorePlay wants to bring in actor-based smart contracts. They're not really smart contracts. I mean, they're more powerful than smart contracts. You could compile smart contracts into CorePlay, of course, and there will be EVM smart contracts in CorePlay that just recompile into PVM code. But we can do better than smart contracts. We can actually do, like, actors, right? So bits of code that just have continuous execution. As far as they're concerned, they don't know that Jam is packing up the virtual machine, storing it in a DA system, and then getting it out again the next block and reconvening them. They don't understand this. They don't know that they're being moved around between cores, parceled up with other actors that they happen to want to be next to. Right? As far as they're concerned, they just live in a big shared state that's always running. Yeah? And the Jam and the Jam service takes care of all of the nitty-gritty. With this, we can have something that is otherwise very hard to do. We can have effective global atomicity. Now, it's not really global atomicity in that we can't have literally all actors kind of atomically interact with each other at the same time. That's impossible. But what we can do is allow for there to be a payment system, in effect, an economy of atomicity. So different actors can pay to be atomically composable with other actors at any given time. And then we have a distributed system that works out the economically best partitioning at any given time. And of course, it would be in their interest because they would take some of this payment. We have zero persistent fragmentation in this model. Yeah? There is transient fragmentation, but it's fragmentation that doesn't matter because those actors that are sitting in fragmented positions of state don't want to interact with each other. That's the presumption. Now, of course, if it's a busy time and there's, like, I don't know, a really popular DEX and everyone wants to interact with it, it will mean that some actors won't be able to interact with it as quickly as other actors. They'll either have to be asynchronous and send a message across to be later processed, or they'll have to wait their turn to do a synchronous composition when they share the same processing core. Or they have to pay more. But this is the sensible, resilient Web3 attitude to managing the need for partitioning state. We don't do it in a static, fixed, permanent partition. So how do we manage to build this thing? Well, Jam, obviously. The fact that Jam has pipelining, this distributed decentralized data lake, a PVM, allows us, these are all the components that we utilize to build CorePlay. One of the very important things of CorePlay is that the individual state machines are not blockchains. They're not these hulking great multi-gigabyte state things. They are actors, small bits of smaller state machines. This allows them to float around a lot easier. We also have regular repartitioning, right? Every 6 seconds, potentially even shorter, but for the easiest way of implementing this would be to do it on the same time frequency as Jam. And we introduce economic, efficient co-scheduling. We co-schedule, we bring together the actors that actually benefit economically from being together, not just the actors that happen to have a team that launched them on a particular blockchain. So there's a few, like, I don't know, alternative, like, there are a few other currents happening in blockchain, particularly in the Ethereum ecosystem. And I want to just sort of compare and contrast the jam approach to these sort of, not alternatives, but other currents. One possible thing is to do is a bit mad, actually, when you think about it, but just actually have different instances of the same code across the different L2s or networks or whatever, partitions. This obviously doesn't work in the same way that we would do with jam, with a single instance. Essentially, we're always dividing the resources, right? It's all very well having the same code, but it's not going to have the same capital behind the code, yeah? Two different dexes, even if it's the same code of the dex, but if they live on different networks, they're going to have different, spreads and all the rest of it, liquidity. Another sort of current in the Ethereum space is co-sequencers. Basically, having the same machine build blocks on two different networks. And then those blocks, because it's being built by the same machine, they can be what I would call causally entangled. Basically, something can happen on one that is dependent on something else happening on the other. Causal entanglement. Now, in effect, that's actually what CorePlay is doing. It's just working instead of with co-scheduling blockchains, which are hulking great things, but with small state machines that we call actors. The reason it doesn't work as well with big state machines like blockchains, essentially, is because it has this huge centralization bias, because blockchains are so big. They have so much state. And everyone that wants to be a co-scheduler has to basically be a full node or a validating node for all of the blockchains that they want to co-schedule. And if we want to do something where we would potentially want to co-schedule anything within, say, 341 blockchains, which is the sort of scale that CorePlay is working at, would have to be a validator node on 341 networks, which is rather unimaginable, and would require a major sort of supercomputer. The other problem with co-sequencing is that entangled cause and effect needs to be essentially finalized on every participant, on every chain that has some effect from the shared cause, or none. If it's finalized on one chain, but not finalized on another chain, or even worse, finalized on 340 chains and not on the 341st chain, then you have a big problem. You've got probably money for nothing. Someone's lost something, yeah? It corrupts the sort of meaning. And what this basically amounts to is that you have to have order n squared in terms of light clients, because every chain has to check what every other chain is finalizing. Yeah? Now, if you've got two chains, it's not too hard, because it's just one. Each chain just looks at the other one. But if you're wanting to really scale this up, or out, then that grows a lot. And that can become a big issue that we manage to avert in Jam because everything's under the same security umbrella, under the same state. Another possibility is like trying to use intent solvers. I mean, intent solvers are fine for what they are, but the main issue is that they don't actually allow atomicity or synchronous composition. They do something a little bit different. They essentially take a problem that you want solving without saying how you want it solving, and then sort of go away and solve it. But it might be that there isn't a user that wants to solve a problem. It might be that two smart contracts just decide that they want to do something. Yeah, and for that thing, they need to be co-scheduled. This wouldn't much help. The final point to note is I haven't mentioned ZK much beyond our block production system. Why are we not using ZK? This is like something that some of the Ethereum researchers seem very, very keen on. In essence, because ZK is really, really expensive. It doesn't make sense, economic sense, at this stage to use ZK technologies as a scaling solution specifically. As a privacy solution, can be very useful, and indeed we're using it as a privacy solution for block production, and a couple of other bits that I'm not going to talk about yet. But for scaling computation, not so helpful. I mean, it does work, and if you have enough money to throw at the problem, then you can make it work at the sort of scale that would be kind of potentially a bit helpful. But it would cost about, at our last calculation, and this is like a little bit out of date, but still, it won't have changed that much, about 2 million times more expensive to use ZK to scale computation compared to using crypto-economic mechanism like ELVs to scale computation. 2 million times. Now, it's probably gone down by maybe an order of magnitude, because we did this like a year or so ago. But still, it's a lot. It doesn't make economic sense to just throw that money away. Yeah? Make everyone pay for it. Especially when we want to do the sort of computation, like PVM, where regular software engineers can use regular languages and regular approaches and regular patterns and regular primitives in order to write regular software that just happens to be running on a decentralized computer. Yeah? Now, there might be a time in the future, and it could be 3, 4, 5 years, where ZK starts to become maybe more sensible. I suspect it's going to be a bit longer than that, and there are some important sort of writings about ZK and crypto economics, one of which you can look up. It was Rob Habermeyer wrote it. That essentially makes fairly convincing arguments that actually ZK scaling is never going to economically outperform crypto economic scaling. Now, one of the big issues with ZK is that it has a pretty high centralization bias. The creation of zero-knowledge proofs requires substantial hardware. I mean, if we want it to happen in a sensible time, like similar to Jam, like 6 seconds for 5 seconds of computation, we're talking like mad levels, like AI investment levels of GPUs that we need to use for this time. This is, this requires huge upfront capital. So even if the chain could pay for that, we would have very few providers. It's a winner-takes-all game, right? The second proof is totally worthless after the first proof, yeah? Which means if you have a strong confidence, you will be the first one to produce the proof, it's worth the investment. But if you don't believe that, yeah, because your machines are maybe just a little bit slower than the other guy, then it's not worth doing anything. It's not worth lifting a finger. And this is the issue. We end up with just a single provider of proofs, and this puts a potential centralization flaw into the network. Good. That is the talk. Thank you for your attention. I'm happy to answer any questions. I think we have, do we? We have a microphone?
Yes. Can you hear me? Yeah, okay. All right, I mean, if you want to, you can still do the demo. But
yeah, all right, yeah? Easy. Right. Let's do it. So, before we go into the talks, let's do a quick demo. So I want to show you a little bit, actually you probably can't see this, can you? It's too small? Can you read that? Or too small? Yeah? No? Yeah? All right, I'll make it a little bit bigger. This is where it gets hard to hold the mic and type. My one-handed typing skills are going to get tested. Okay, let's open demo. Oh, no. So what I want to show you here is an example Jam service. This is what it looks like to write code on Jam. As you can see, there are the entry points whose names you should by now sort of be vaguely familiar with. Refine and accumulate. Refine is the thing that does all of the heavy lifting, pre-processing, and so forth. In this case, it's just giving us a debug remark that will come out and be printed to the console, and it's actually fetching the authorization output. Something I didn't mention, I skirted past, was that authorizers, in addition to checking that the work is allowed to be done, can also give an output. This actually is very, very useful, very important for some particular use cases we have in mind. But basically, the authorizer can pass some data into Refine for Refine to act on if it so needs. There is then we then sort of get the payload as well. Every Refine obviously has data coming into it. That's the payload, and all we're doing is passing. Actually, we're putting the payload into our distributed availability system. That's the export slice thing there, and passing the ID that we got with the output into accumulate. And accumulate's going to pick these up again here, and then put two things in memory in its storage. One of them will be the last payload ID, and that will store the payload ID, so we can find it in DA and in our storage system. And the other thing will be the last auth output, which is the thing that came from the authorization agent. Now, if we look at the authorization agent, let's have a look. No, that one. Null auth. So this is a very, very simple authorizer. Authorization agents or authorizers can take a parameter that they're sort of parameterized with. It just sort of configures them, if you like, kind of a configuration setting. And then they also get given the work package, which, amongst other things, contains the some sort of authorization token, something to prove that this is legitimate work to be done if the work in the package itself doesn't already prove that. It's like an extra bit of data that you can put in there. It might contain, for example, a signature or something. Maybe a zero-knowledge proof, maybe a Merkle proof, who knows. All we're doing here is checking this authorization data is the same as the thing, the data it's been parameterized with. Very easy. If it's not, it says it's failed. Authorization failed. It doesn't authorize the thing. Otherwise, it just passes the parameter out into Refine. Now, we have a nice, I've been working on this last week or so. We have a nice little REPL. I hope it still runs. I haven't tried to try it recently. Ah, good, it does. So this is this creates a jam network, right? So it's running jam now, and rather than producing blocks every 6 seconds, because that we don't want it to do that. It's too many blocks. We just produce a block when we're doing something. Yeah, and rather than having lots of auditors, we don't bother auditing. We would normally audit to make sure the work is correct, that the work that's being made correct is correct. We've turned that off, so there's not too much, it's not, using too much CPU or anything. Good. If I want, I can, for example, extend the chain by a block, and it's authored a block, and then we can see that the block is now 1, whereas before it was on the Genesis block, 0. We can look at the services that are already deployed. There's actually only one service deployed. It's the service 0, and it's the Bootstrap service. Now, one thing I didn't mention in the talk, well, purposely didn't mention, is that Jam has no way to directly use Jam, right? As a user, it doesn't have transactions. As a user, there's no way of literally using Jam to create a service unless there's already a service that wants to create a service, The only thing Jam runs is this service stuff. It progresses the computer. It doesn't have a sort of user interface or a BIOS. Yeah, Jam, if you like, provides virtual hardware, virtual silicon, like a CPU, memory, storage, whatever. But it doesn't provide the software or even the firmware that runs on that virtual hardware. You have to do that yourself. So one of the things that Jam starts with is called the Bootstrap service, which is a bit like a basic operating system, or like the BIOS. If you remember, PCs, they have this BIOS thing that loads the operating system and allows you to do stuff. It's like this initial piece of software whose only real job is to let you deploy and run other pieces of software, because Jam itself doesn't do that. If you compare that to other smart contract systems, they come with this stuff built in. But the problem with having it built in is it sort of creates problematic opinionation that oftentimes, as time goes on, you realize, actually, I wish we'd done it this other way because that would have been more flexible. So with Jam, we try to avoid opinionation as much as possible, which is why we do it this way. Okay, so we have this bootstrap service. It's like literally it's a real service. I could show you the code, but it's basically just a big match statement that just tries to match on instructions and then actually executes the instruction. One of the things that we can do is create a service. Now I've already compiled the demo service, the code that's there on the left. And it's, I think, called demo service.pvm. So what I'm going to do is invoke the boot strap service and create a new service with demo service. I think that's what it's called. And then we specify like the minimum gas that is needed for a couple of things, but I'll just use 0. We don't really need that. Some sort of balance. I'll give it, I don't know, let's give it 42 lots. And then some sort of memo for the creation and this initial balance. We'll just put a hello. I think that's right. Let me just check that on my cheat sheet. Yes, that's the right order. Yes, we actually have to pass a hash as the service code. So the percentage just says, take the data and put it through a hash function. And there we go. So we've now created a new service. So now if we list the services, we have 2 services on Jam. We have the first one, the bootstrap, and then the second one, which is, it's got this long number. So instead of using long numbers, we allow you to use letters. So first one is going to be called A. And you can see there it's got some balance and some, it's telling us that the code is demo service and so on. The reason the balance isn't the same as the balance I put in is because it automatically adds some extra balance to look after the fact that you need some balance to store the code. And that's why it's an odd number, because it's basically 1 unit of balance per byte in the code or something. Good. So now we can do something. We can like maybe send we can invoke this service. We can send it a piece of work to do, like we would invoke a smart contract with a transaction. So the way that we do this, we actually construct a work package. First, we create a work item, which I think I can do this, yes. And then we say, it actually will go by default to this service. We actually have a concept of a default service, which is A, as we've been told. So all I need to do is tell it what the payload is, and I could say something like hello HK. Okay, good. We have 1 pending work item. Now, we haven't made a work package yet. This is just one of the items in a package. Little bit like transactions in a block. So before in order to make the actual package, we need to make the package and guarantee it. So we just have this command guarantee. And this is going to use a default authorizer, which basically is the null authorizer. And we happen to know this is on the first core. The cores are already prepped for basically saying that if you use the null authorizer, the work is valid. So we have, as you can see, it's gone into the null authorizer, seems okay, and it's got into refine in the demo service. That's good. That's our new service. Hurrah! With the payload hello HK. Very good so far. And we have a trap. Oh dear. Okay, so the demo service, as you can see, has panicked in its refine. Now, this isn't like a big issue. Yes, this isn't a big issue. But the reason it panicked is because we made an export without telling it. Actually, we have to sort of tell it we're going to want to export some information. And I think we do this, if I remember correctly, with 1. It's either 1 or... No, it's not that. Okay. And in that case, it's the second item. There's a second parameter. So what I'm going to do is just restart this and pop it in there. So we're making the service again. Very good. Now we're going to do work item. And then it's sending to hello HK. To the default service, which is A. And then we have to tell it we are making one export. Good. Let's guarantee that. And there we have it. So that didn't panic this time. We've told it the correct amount of exports that we're making. Sort of like a resource, the ability to export data. And this is exporting it into the distributed availability system. Okay, now we can read memory with the read storage command. Now we're going to read if we remember, we put two things in storage, last payload ID and last auth output. Let's look at the last auth output first. This should be empty because our authorizer didn't have a parameter. But it should be something, but just empty. There we go. If we read, for example, something else, it will say it's empty. So we know it's put something in the storage. Now, if we want to look at the payload, we're going to have to look at the payload ID. Now, this is a integer that has been encoded into storage, right? So it's going to just be 0 because the payload ID is just all zeros. So it's just going to tell us it's zeros. And there you go. It's the empty string with 8 zeros after it. That means it's 0. So how do we actually look at this? Well, we want to list the segment trees. And there you go. We see that in our work package, which has some particular segment root, there is one export, which is which says it's index 0, and it says hello HK with, it turns out, a bunch of zeros after it, because of course segments are 4K or thereabouts in size. Good. We can also make a transfer. So we do this with boot transfer. Now, I can't quite remember the order of parameters here, and it's not going to tell me. Okay, fine. Then let's look into instruction. I just have to quickly find the, where are we? Here we are, parsing. So we can see transfer has destination, amount, gas limit, and memo. So the destination, we want to send it to A. The amount, let's send 42 over. The gas limit, was it? The gas limit would give it plenty of gas. And the memo, we will give it hello HK again. Actually, let's do it something else, otherwise we might get confused. Say money for nothing. Boot transfer, cannot process array. What's our array? Might need to do something to this. There we go. Okay, so what's going on here? Well, we're sending a work package to the Bootstrap service. The null authorizer is executing, make sure it's all good. It is all good. So now we're into the Bootstrap service. Refine is happening. And then it goes into accumulate. Accumulate sees that there is a transfer instruction. So it's attempting to do the transfer. It got a result. Okay, that gives us some confidence that transfer actually went through, at least according to the Bootstrap debug log. And then actually we have this other message that has come from the demo service. Here we are, which also says that it's got a transfer. So that's also looking very promising. Let's have a look at the demo services storage. So let's go back to read storage. And we're already, our default service is the demo service, so we don't need to pay too much attention to that. And I think we have something in here. If we go to the code, it's setting the storage last TX to this message that we've formatted. So it should be a nice message that we can read now. So let's have a look at the storage item last TX. And there it says transfer. At block 7, from 0, that's if you remember the bootstrap service, to us, that's our long thing, that's actually A's ID. Of 42, good, that's the amount that we wanted to send, with a memo, money for nothing. Good. Okay. I could demo a bunch of other stuff like authorizations and things, but I think it's probably time better spent to take questions.
Yeah, thank you very much, Gavin, for sharing all your insights about Jam, but also Web3 in general with us. Please, let's give Gavin a big round of applause. Thank you. All right, so now Gavin will take a few questions from the audience. It will be one question per person. Please make it technical. All right, who wants to go first? Maybe here.
Switch the slide. Hello, hi, Gavin. I think you just mentioned the speed of PVM is about 45% of 86 natively. So how would Ethereum in this case, if we put into the comparison? And I would assume it's way slower. So if given this case, can we directly write an emulator to let all the EVM contract can directly run in PVM?
Yes.
Do you like this idea?
Yeah, I think it's a sensible idea. I mean, there's two ways of attaining Ethereum compatibility within a PVM execution environment. One of them is, as you say, just recompiling EVM code. This is like the sort of lower level way of doing it. The higher level way of doing it is retargeting Solidity, which most EVM code is written in. This is what we are currently doing. So we have a Solidity to PVM compilation pipeline, and it works very well. It's like highly compatible. It might be even 100% compatible. And it works better than recompiling EVM bytecode into PVM, mostly because EVM bytecode is itself quite inefficient for what it's trying to do. Like, it does more stuff accidentally, just because it's, like, for example, you want to add two 32-bit numbers. Well, you'll be adding two 256-bit numbers, and unless you know for certain that their maximum is 32 bits, that they're not going to use the other bits, then you have to compile that into a 256-bit addition, which is obviously quite inefficient. It's also big endian, and whereas PVM, like basically all modern hardware, is little endian. So you also kind of have to faff around with a lot of stuff that's like built for big endian. Whereas in principle, if you're just recompiling the Solidity, some of the times you can get away with having things be stored little endian, or having things be in little endian. There's a few other sort of gotchas that make recompilation of EVM to PVM less, just worse than compiling the Solidity to PVM, as you would expect. But it's still quite a lot faster than EVM.
Thank you very much for your question and your answer, Gavin. Right, more questions?
Okay.
Has some?
Okay, I have just get the microphone. Hello, Gavin. I am a student from China, so I have a question to ask you. I wonder that how can you deal with long-term data storage, because the knowledge of human society is growing exponentially. And do you think that a 2 petabyte data pool is enough? Or if we have to deal with kind of storage bottleneck in the future, how will Jam deal with such a bottleneck? Or perhaps it can just delay the bottleneck instead of break the bottleneck?
Yeah, it's a good question. I mean, as Bill Gates said, 640 kilobytes ought to be enough for anyone. No, I mean, of course, the 1.6 petabytes is, I mean, it's big by blockchain standards, by today's blockchain standards. It's very big, but it's not going to last indefinitely. Now, I haven't gone into this in this talk, but one of the things that Jam is built for is composition of different instances of Jams. So Jam, as I sort of mentioned in that, like, alluded to in that how to build a Web3 cloud slide. Well, you start off by building a Web3 computer, right? A fast one, a good one. But also one whose execution model refine, accumulate, can reasonably be scaled out over multiple cores and in principle, multiple machine instances. You could in principle therefore take 2 jams and have refine run on one and accumulate run on the other. Like the data that goes from refine to accumulate is pretty minimal and refine is essentially stateless. Yeah. Now what this means is that you can scale the jam model beyond a single instance of jam. Not all the questions have been answered. I don't want to like suggest that this is already sort of ready for building, but the basics are sort of there. This would imply that the different jam instances could each have their own 1.6 petabytes of DA. And then if you have many jam instances, you could scale up this DA, but still make it basically part of the same shared state machine. Probably using a DA system on a remote jam instance would introduce higher latency. So there's going to be some affinity for which machine you actually run your code on, as you would expect. But in principle, it should be elastically scalable. Now, the 1.6 petabyte isn't meant to be a permanent storage. It's immutable, but it's actually immutable but non-permanent, which means data sticks around. It doesn't change, but it gets flushed after 28 days. If you want the data to remain after 28 days, you basically have to either use a different storage system or refresh by sort of rewriting it into the DA. So that 1.6 petabytes is the amount of data we expect it to be able to store over this 28-day period. Yeah, and that's why it's like actually sustainable, because we don't try and solve the unsolvable problem of like actually storing all of humanity's ever-growing data. But it might very well be that there is a service that gets deployed onto Jam, which very sort of fluidly and succinctly integrates into Jam's DA and provides longer-term storage for, if you're willing to pay for that long-term storage. Something a bit like Filecoin, basically, where you can kind of tag this data. If it's going to be chucked out, if it gets to 27 days and it's going to be chucked out, then actually please store it in this long-term file storage, and here is some payment for that to happen. And then if I ever need it, please get it back out again automatically. But that's not part of the main Jam protocol.
Okay, thank you.
You're welcome.
Thank you. Okay, we have time for one more question. Who has a very good question? Yeah?
Thanks, Gavin, for the amazing overview of all the new stuff that you're doing with Polkadot. My question is to do with user, developer experience. And you were just doing a hello world, which essentially just printed a hello message. But there was a lot of steps, there was a lot of code. Is there any plan to have like a higher level language where, for instance, if I want to do a hello world, which just prints a message, I could just do it in 5 lines of code and not have to worry about a lot of these other things in the middle?
Sure. Yeah, I mean, developing on Jam itself, like developing services on Jam is a pretty sophisticated protocol. And it was developed in large part as a useful stepping stone from where we are now with the Polkadot relay chain to creating something that we could implement both Polkadot relay chain functionality on, like securing parachains, L2s, whatever, and implement CorePlay on. And essentially Jam is sort of the minimum changes that we could make from more or less what Polkadot is into something that could be this elastically scalable actor smart contract system. Now, CorePlay, I can't give a demo because it's not written yet. Some stuff is written, but in particular the dynamic composition isn't written. In the not too distant future, I will be able to give a demo of writing a regular function main print hello. I mean, it's probably going to be more like a file thing because there isn't a monitor to print hello onto, right? But probably like an open DA storage, output this to DA storage. And that will be compilable by a regular compiler. I can write it in C or C++ or whatever. And the compiler will just be expecting a regular computer minus all the STDs, like all of the, I/O and whatnot. There'll be specialized I/O because it is a specialized machine. But it will look very much like a regular program. And this would sit in a jam service, not be a jam service. So there will be a jam service designed to run regular software. Software that can have a loop. Yeah, it's actually unfortunate. I might change the demo in the future because we already have a PrimeCiv demo that's running in a jam service that's just regular code that just finds prime numbers, and it's just an infinite loop. And so this runs over block, over block, over block. As far as it's concerned, it's on a continuous machine. This would be a fairly simple bit of code that you might see in a sort of a graduate, or maybe undergraduate, like kind of maths, introduction to programming maths. And yet it runs on chain. And this is very, very much what we're aiming for. The reason that, it's just jam, as I say, is this platform on which this kind of thing can be created. And it doesn't really make that much sense to try to make it monolithic because we want to remain somewhat flexible over how this higher level portion is implemented.
Thank you. All right, before we move on to your next steps, I would like to give us all a last round of applause for Gavin for coming here to Hong Kong today. Thank you. Thank you very much, Gavin. Okay. So you might wonder now, so I heard now about jam, about what Web3 truly is. So how can I contribute? How can I be part of jam or the Polkadot ecosystem? And so extra for you, we created an overview. And please, no one leave yet, because we will have a networking session right after. So there is jam chat on Element. You can also attempt to read the gray paper. It's quite technical. Then we created a very simple overview. It's called Portal. It basically summarizes all the resources to get funding, to get started in the Polkadot ecosystem. As with the Jam Tour, we are really trying to find developers, and that's why we are going around the world to build the future use cases on Jam. So we just came here from Mumbai, where we had like 200 or more, I think 250 students hearing about Jam. So yes, please check out those resources if you are interested to learn more. And also, you can apply to a new course which the Polkadot Blockchain Academy is building extra for Jam. It will be launched towards the end of the year, and it will be in Bali. So please check it out. And yes, and also please apply for the hackathon. All right, so right, with this, I will then wrap up our session here, but I would like to continue our discussion over there in El Charro. We have Mexican food, snacks, we have a lot of beer there, so please join us so we can talk more and answer your questions. And yes, and I would also quickly like to thank again our partners, Cyberport, as well as Polkaport East, for the venue and helping us with the organization, as well as our community partners, OneBlock Plus, EZA, Papermoon, and Edge Distributor SubDAO. Thank you all very much also for coming here. Thank you, and see you in a bit. this one too. Yeah. Thank you.